Welcome to Section 1 of Biostatistics. In this section, we will provide an overview helping you to build a framework for the numerous topics so you can apply them appropriately. Let's get started. There are many ways to approach biostatistics, but the main thing to understand is that you are trying to study a disease and apply that understanding to the patient. A good way to think of biostatistics is in three basic arms, or steps. First, a study is designed and performed. Second, the study is evaluated. And lastly, you appropriately apply the study to the patient. So first, a study is designed and performed. And you get tested on this aspect by understanding how various study designs are performed and what information they offer. For example, cross-sectional studies, cohort studies, case control studies, and randomized controlled trials. Next, the study quality is evaluated, and you get tested on this aspect by understanding type 1 and type 2 errors, confidence intervals, as well as statistical tests used for evaluating statistical significance, including the two-sample t-test, the ANOVA test, or a chi-square test. You must also be able to identify confounders or biases that may be present within a study. Lastly, you apply the information from the study to your patient or to your understanding of the disease. And these elements include the sensitivity and specificity of diagnostic tests, the positive predictive value and negative predictive value of tests, likelihood ratios, incidence and prevalence, and risks of disease associated with exposures. Now, we will teach you how to dominate all of these elements in the 9 sections of biostatistics. Now, before you go into those sections, let's dive into some specific terms you will need moving forward. Let's start off by talking about the mean, median, and mode. The mean is the average number in a data set. The median is the middle number of a data set, and the mode is the most common number in the data set. With normal distribution of data, so a normal distribution curve, a bell curve, or Gaussian curve, the mean, median, and mode all equal each other, as you can see here. Let me draw this out briefly to show you why. So along the y-axis, we have the number of data points. And then you have the x-axis providing the range of results. You have the high end and the low end. In a normal distribution of data, most of the results will appear here in the middle, which is why the peak is highest here in the middle. So let's do an example. For this example, let's say that the x-axis is systolic blood pressure in millimeters of mercury, and this point right here in the middle will be 120 millimeters of mercury. Now let's find the mean, median, and mode. The mode is 120 millimeters of mercury. The mode is always easy to spot because it is always the peak of the graph. You want to find the most common number, or the mode, just go right to the peak. Now the mean is also 120 millimeters of mercury. Why does this make sense? Well, we already established that the most common number is 120, and since there is equal distribution in this graph, the results on the right side will equal the results on the left side of the mode. And we would expect these to average out to the middle, or where the mode is, which is 120 millimeters of mercury. And finally, the median, the very middle number, is 120. And since this is a normal distribution, you can assume there are as many results on the right side of the mode as there are on the left side. Now, data does not always produce a normal distribution like we just saw. For example, in a negative skew of data, the graph ends up shifting to the left. You can see this leftward shift most clearly if you focus your attention on the mode, or peak of the graph. Picture this point as the middle of the graph. Then you can easily discern where the data is skewed. As you can see, the left side of the graph, or more negative side of the graph, has more data, at least more than the traditional bell curve, which would look something like this. Now, when the results of a study show a negative skew, you will see changes in the mean, median, and mode relative to one another. Now, the mode is always the easiest to find because it's always the peak, the most common number. The mean, however, is shifted to the left. As you can see, there is not an equal distribution of results on the right and left of the mode. There are more on the left over here. So it is reasonable to expect the average to shift left. Lastly, the median is defined by the middle number, and it falls between the two, right here. The best way to remember the placement of these three terms on a negative skew is to repeat in your mind mean, median, and mode in that order. And you always start from the high end of the skew, or the end with more data. So in this negative skew, we start from the left, where the data is higher, and say mean, median, and mode. And by so doing, we found how these changed relative to one another on a negative skew. In a positive skew, more results show on the high or right side of the graph. So how did mode, median, and mean change relative to one another? As always, the mode is the peak, or the highest number. And since you know the terms are always mean, median, and mode in that order, always starting from the high end of the skew, in this case on the right side, you know where each should fall relative to one another. The mean is farthest to the right, then the median, then the mode. Now let's do a question to apply this. A study is performed in a family medicine clinic in which the HbA1c is measured in otherwise healthy males between the ages of 20 and 30. The HbA1c results range from 4% to 5.3%. However, an unusual number of new patients have HbA1c ranging from 3% to 3.5%. How would the mean shift in relation to the median and mode? Let's again picture the bell curve with HbA1c levels along the bottom. We are told that the population that attends this clinic have HbA1c levels ranging from 4% to 5.3%. However, we are told that there is a big number of new patients that come in with HbA1c levels ranging between 3% and 3.5%. So this data would be added to this left side of the graph. So our graph actually looks something like this. So this describes a negative skew. So we'll just erase this line to make things cleaner, and just remember that our new patients appeared on this left side. So now let's find each of the terms, mean, median, and mode. And the mode is always the easiest one to spot because it's always the peak. Then starting from the high end of the skew, we repeat mean, median, and mode in that order. And the high end of the skew in this case is the left because it's a negative skew. So the mean would be somewhere in here, and the median would be between the mean and the mode. Now let's talk about standard deviations. The math for standard deviations is ridiculous, and thankfully, you don't need to know it for step 1, or even to be an excellent physician. Just know that this symbol, sigma, represents standard deviation. Now the standard deviation is valuable because it measures and tells us the variability of data compared to the mean within a study set. This will make more sense in a moment. It is important to know that one standard deviation from the mean encompasses 68% of the data, while 2 standard deviations, or technically 1.96 standard deviations, encompass 95% of the data, and 3 standard deviations, technically 2.58, encompass 99% of the data. To show you what I mean, look at these 2 bell curves, each representing systolic blood pressure along the x-axis. The mean, or average of both groups, is 120. Now let's say the standard deviation for the graph on the right is 5 millimeters of mercury, but the standard deviation for the graph on the left is 20 millimeters of mercury. As you can see, the population on the left has more patients falling away from the mean. Another way to say this is that there is high dispersion of results on the graph to the left. Conversely, with a lower standard deviation of 5 millimeters of mercury, you will have less dispersion from the mean. In other words, more of the data points will be clustered closer to the mean. So we're coming back to the standard deviation slide with a few additions. So the take-home point is that higher standard deviation indicates higher variability and higher dispersion. In other words, more results are distant from the mean. And just barely, we were referring to a single standard deviation, which correlates to 68%, which we discussed before. What I want to draw your attention to now is that if one standard deviation encompasses 68% of the data, that means that 32% of the data fall outside of one standard deviation. Likewise, if 2 standard deviations encompass 95%, then 5% of the data will fall outside. Same applies for 3 standard deviations. 1% will fall outside 3 standard deviations. To show this graphically, let's look at the normal distribution. 68% of the findings fall within 1 standard deviation. This right side would be positive and this left side would be negative. 95% will fall within 2 standard deviations, 2 above and 2 below the mean. And lastly, 99% or 99.7% fall within 3 standard deviations, above and below the mean. Now let's do a question to apply this. A study of 200 elderly males between the ages of 80 and 89 evaluates their cognitive ability with the mini mental status exam. The average score out of 30 possible points is 23. One standard deviation is 2 points. How many patients have scores of 19 or lower? To get this question right, you start with the mean and figure out how many standard deviations 19 is from that. So if we're looking at a normal bell curve, we are told that the mean is 23. And since this is a normal bell curve, the mean would be in the middle. And we are told that one standard deviation is 2 points. So we'll say one standard deviation on either side of the mean is depicted here. 2 points above and 2 points below. And our mean is 23 points. So with one standard deviation, our range is from 21 to 25. Now we still haven't reached 19, so we can't answer the question. Let's try 2 standard deviations. This would be an additional 2 points on either side. Therefore, 2 standard deviations give us a new range of 19 points to 27 points. And the question asks us that of the 200 patients studied, how many of them had scores of 19 or lower on the mini mental status exam? Since we know that 19 is 2 standard deviations from the mean, and we know that 2 standard deviations will catch 95% of the data, this means that 5% will fall outside this range, 2.5% above and 2.5% below. Now this is where many students get tripped up. Remember that the remaining percent is always split up above and below the range. So now we know that 2.5% fall below the range. We can take this and multiply it by 200, which is 0.025 times 200. And this gives us 5. So of the 200 patients, how many of them had a score of 19 or lower? 5. So now let's talk about the standard error of the mean, or SEM. The standard error of the mean measures the variability between the mean of the sample, and the sample is made up of n, and the mean of the general population. The math is found by taking the standard deviation, sigma, and dividing that by the square root of n. And remember that n equals the sample size. And it's important to recognize that as n increases, since it's in the denominator, the standard error of the mean would decrease. This is important because as the sample size gets larger, your variability will then decrease. In other words, the results of your data will cluster closer to the mean. Conversely, if your sample size is lower, your standard error of the mean will increase, which means your variability will increase, which means that more of the results of your data will be dispersed further from the mean. And last, we will talk about z-score. Z-score tells you how many standard deviations you are from the mean. This concept is so simple, it's almost confusing, but it really is as simple as it sounds. If you have a z-score of 2, you are 2 standard deviations from the mean. A way you might see this clinically is if your patient has a diagnostic test revealing a z-score of 3, you think, wow, that's 3 standard deviations from the average. And that concludes this section.